So thank you, gentlemen. My first question for you is the topic of battery management systems more relevant today than it has been in the past? Your thoughts?
Sure. So I can dive in. So there's certainly been advancements in battery chemistry over the years. I mean, a lot of people here are involved with that. If we go back, 10 years in time, we didn't have the kinds of lithium chemistries that we have now. And so lithium and many of the other flavors that have come forward provide us additional advantages for specific applications. We get additional energy density. It enables a whole other world of mobile applications that we didn't have in the past. So these are all fabulous things that enable new applications and lifestyles. However, these lithium chemistries require additional management and monitoring compared to their lead acid forefathers. And that means you need to have electronics in there, making sure that those cells don't get damaged, and there's actually cases where those can as much as cause fires. And so we need to make sure that we have appropriate control systems in place in order to gain safe advantage of some of these new battery chemistries.
Thank you, Michael. The topic of active versus passive balancing is something that is floating around the industry. I thought you'd like to talk a little bit about in what applications would active balancing make more sense than passive balancing?
Well, I can tell you from our experience, certainly there's a lot of potential advantages for active balancing. But one clear advantage would just be strictly on a cost basis. For example, we're seeing a lot of interest in active balancing for large cell stacks, and particularly like ESS. And if you think about it, it's really just if the end life of the product is supposed to have a defined capacity, and there's a certain model of expectation that over that life, the variation in capacity will limit the amount of usable capacity in the cells. If you, when you have, for example, a 10% reduction in one of the cell's capacity, that's really going to limit your maximum capacity to get out of the whole stack. If you can use the capacity of the other cells in the stack, you can then keep yourself from having to oversize the stack to make sure that you have the sufficient stack over the life of the cell. So for example, at $2 to $4 for active balancing, if you had to oversize your stack and it cost more than that to ensure that you had the capacity for the life, then active balancing would be a viable option, one advantage for active balancing.
Yeah, I mean, it's interesting how the terms have gotten named as passive balancing and active balancing, because it automatically sounds like active balancing is better, right? Do you want passive? Do you want active? Active sounds better. We joke sometimes in sales calls that they should have been called economical balancing and expensive balancing, because the reality is the active balancing puts a bunch of additional circuitry on the board, which as commented, sometimes it's actually more cost effective just to put a slightly large battery in place in order to achieve the same advantage. Because really what you're getting in active balancing is in an application where your cells are getting slightly out of balance during operation. Active balancing allows you to, of course, shuttle charge from one cell to another, effectively extending the capacity of the battery, so that rather than being limited by the lowest common denominator cell, you actually can achieve better usage of the entire battery. So there are certainly applications where it makes sense, where, for example, if you don't have great individual cell knowledge of state of charge. So for example, lithium is very flat in its voltage for a lot of its curve. It's really only at the high end and low end where you have good absolute voltage data on where that cell is. So there's applications where you're running 24/7 and you never achieve full charge and never achieve full discharge. And in those sort of applications, active balancing can really be warranted in order to balance that pack while in use.
So, do you have any comment, Greg, on the price issue that Michael raised?
Well, as I said, the active balancing typically runs $2 to $4 per cell. If for example, you had to oversize your pack by a couple amp hours per cell, well, then I think you've got a good case for active balancing, just in that aspect. I mean, there are other advantages for active balancing as well, potentially faster charge times. You have less heat dissipation, so you have less restriction on your thermal management. If you have a constricted energy source, where you really need to be efficient, or constricted, footprint. So there are other advantages to active balancing as well. But certainly, I don't think anybody is saying it's a cheap option. It's an option that can offer a lot of advantages in certain conditions.
Agreed. And how does active versus passive impact testing BMS systems?
So in testing a BMS, whether it's active or passive balancing, it's balancing, and you need to test it. And it's best to test it by simulating before you connect it up to a battery. And the simulation is still simulating the behavior of a battery pack. And so that's the most important thing. However, the algorithms are more complex and as well as more expensive for the active balancing. And therefore the testing needs to be more comprehensive, and it takes a longer amount of time. So testing becomes all the more important with complexity, and complexity is higher with active balancing.
Now you're mentioning simulators. Wouldn't you say that the real testing has to take place on the battery, Peter?
I couldn't disagree with that more. I mean, obviously you have to have this, connecting a BMS to a battery without it having been tested, that's dangerous. That's a recipe for, thermal runaway or any kind of safety event. So it's downright dangerous to test a BMS or design a BMS connecting it right up to a battery pack.
Thank you. My next question is, with large-scale battery designs, what methods are being used to ensure that new BMS designs are ready for pack integration before connecting to and controlling high voltages and currents?
Okay, so that leads right into the simulation equation. So simulate, right up from the beginning. Test. So at the very beginning of a large-scale BMS design, when you're prototyping the hardware and designing circuits on a breadboard, you can test it with simulation right then and there. Test the circuits. And then as you go on through the BMS design and you design your first hardware prototype, then begin testing that. And as you design software, you need to iteratively test it throughout the design cycle. And you can test it repetitively, and it's extremely important to model the pack that you're designing the BMS to control, and that's that much more critical with large-scale systems.
Now, for myself, Peter, I'm not really that conversant with battery testing. I know that with electronic design, that we make things called Franken systems because simulators only have limitations. So we really want to test on the real hardware. So wouldn't the case be as soon as you've gotten the safety issues out of the way that really you should be testing on the battery?
So that is a misconception because, well, ultimately at the very end, yes, you need to be testing with a real battery, but you need to assure that all of your algorithms, your state of health, state of charge, all of those things are working, the balancing is working, and a real battery pack changes its properties with every charge and discharge cycle. So literally, each and every cycle that you use it, you're going to have different behavior slightly from cycle to cycle. And so it's not a repeatable test. So the only way you can have repeatability is if you have known characteristics that you're testing against every single time. And that's not possible with a battery pack.
Yeah, having built 4 generations of battery management systems, I can chime in here. So I mean, we use the Bloomy BS 1200 to test our battery management system. It was great because, as correctly identified, we need to be able to test all the different corner cases of the battery management system. So does the BMS respond correctly when voltage of cells get too low? Does it respond correctly when voltages get too high? Does it respond when temperatures get outside of appropriate ranges? Does it respond when currents get outside of appropriate ranges? Each of these corner cases have to be simulated, and they have to be simulated in all sorts of different parameters, you know, while charging, while discharging, and everything else. And of course, we can't test that on real cells because it would physically damage the cells, and you know, people discourage test beds burning down in labs. So it's better to do that in simulation. And I think, as Peter pointed out, you know, we do, you know, some 80–90% of our testing in simulation, and then when we get to the final test, like for example, if we want to rigorously check a state of charge algorithm against the actual battery cell, then we run it against the actual battery chemistry in order to kind of do a final conclusive acceptance test. But it's certainly way faster in order to run, and we have this fancy robotic algorithm we run. It's way faster to run that with simulated batteries rather than physical cells.
Thank you, gentlemen. I'll change topics a little bit, especially in one issue that is impacting large-scale systems particularly, are cost and pack range and lifetime. And so my question is, how can BMS electronic design decisions minimize cost, maximize pack range and lifetime, and ensure safety?
Well, that sounds like a perfect question for me, because that sounds like taking off my marketing material. So, so I think all of those issues that you mentioned really are, those goals are all maximized really by considering the same thing, and that is how accurately you can control the operating conditions of your cells. And so we're talking state of charge and state of health, and the more you can really accurately know where you are, the more you can fully utilize the capacity of the cell without exceeding either the top or the bottom range, in which case what you'll do is you'll tend to age the cell. If you put too high of a voltage on it, you'll really degrade the cell, in which case you're now limiting the capacity and degrading its age. So how do you do that? How do you really actually know where that cell is? When you're talking about a stack of cells that are operating in some high voltage stack, and what you need to know is, I mean, obviously understand your chemistry, your form factor, all the environmental conditions those cells are operating in, what the current through the cells are, the temperature, and the voltage. And the voltage is actually one of the more difficult measurements to make on a stack of cells, especially if you have a high voltage stack and what you're trying to do is measure a differential signal all along a few hundred volts. You've got a big common mode issue. And typically, for example, in an automotive environment, you've got inverters, chargers, all kinds of demands on the battery that are creating incredible noise. And you're still wanting to pick off to within a few millivolts of accuracy that differential signal along that cell. So, you know, what we do at Linear Technology is we make high performance analog ICs, and we saw this as a difficult problem and a problem that would be, you know, right for us to pursue. We've been making these battery stack monitors since 2008 on a 3rd generation part. What it does is it monitors 12 cells in series, each one of these parts, and measures the voltage to within 1.2 millivolts of accuracy. It's designed to be able to measure that voltage under a lot of noise. It's designed to be able to measure it day in, day out. Keep that accuracy, you know, after you've soldered it on the board, after it's been through temperatures, after it's been aged, throughout the life of the batteries. So the batteries are supposed to last 10 years, so you expect that you're going to be able to manage that and accurately determine where you are operating those cells over the life of those cells, so you can maximize all this. So if I would sum it up, I would say if you want to achieve those goals, focus on accuracy when you're designing your BMS. Focus on being able to, as accurately as possible, to determine the conditions of those cells throughout the entire operating of those cells.
Thank you.
Yeah.
So there are a number of different architectures for a battery management system. Fully distributed, completely centralized, modular. Some people advocate one versus the other. What are the pros and cons of these systems? And what would you advocate for particular applications? This is a general question to the panel.
Sure. So, I mean, chiming in on different architectures, I mean, we're system engineers, so we work on a lot of different battery applications. There's times where a fully centralized battery management system makes sense. Those are generally smaller batteries where you have a single circuit board that's talking out to perhaps in the range of 12 to 24 cells. And then it makes sense to put it all on one circuit board and you've got a single centralized system. We generally find that above about 24 cells, you're breaking this out into a distributed system because the master has all the intelligence on it. So it's got the expensive processor and all that sort of stuff on it. Whereas the slaves can be pretty unintelligent, no insult, but it can be pretty unintelligent analog front ends that really are just doing analog sensing and responding to commands from the master. And that ends up being a more cost-effective topology. Further, it ends up, there's just a physicality of batteries because they have volume and they have weight. And so you want to have these sense lines for your batteries as close as possible to where the batteries are to get a nice low resistance connection. And so you actually end up wanting to, once you get above a certain size, you want to distribute your cell interface modules and have them close to the actual battery terminals. And so there's also a physicality that makes sense to distribute them. There are corner cases where it makes sense to have a fully distributed setup. So this is where you're actually measuring each individual cell. We haven't seen those so much in industrial applications. Those have been more for hobbyist sides. There tends to be a lot of wiring and labor involved in those kinds of applications. So those are the three. Did I hit the primary architectures, or I think we go?
So I'll chime in on that a little bit. So the idea of a fully distributed system is kind of attractive just fundamentally because what you've done is you're saying on each cell I'll put a set of electronics and I'll make that my base building block, and then I'll just use many of my building blocks for whatever size I want. So conceptually it sounds nice. Some of the models, I've never really seen any large-scale production of a fully distributed, system, but the idea has been around for a long time, and you could imagine that they are daisy chained. That's the proposal for some of these systems, so you can simplify the wiring. But I think the real problem is that you've got a cost issue because duplicating a set of electronics for every one of your devices. Potentially a reliability issue too, because instead of this reliability of one set of electronics, now you've daisy chained a whole bunch of them that each one now has to be working. So you've got potentially reliability, but fundamentally I think the biggest issue is the cost. You're not really taking advantage of the integration. For example, if you move to the modular level where you have something like 8 to 24 cells in a module, you can take advantage of things like the battery monitor that we make, which includes the integration so that you can monitor 12 cells with one chip. And you also get some advantages for working at that level as well. So if you're working cell as your basic fundamental building block, your system's not looking at groups of cells. In a module it is, and that's good for example, redundancy. If you want to measure your module of cells and compare that to the sum of all the individual cells, you get some advantage. If you want to do active balancing, you can move charge around within the module. So there's some advantages to the module level where you're getting the basic building block, which you can use as a fundamental element. If you're a manufacturer with multiple models, you can take these and build different size packs as you need. And as Michael had said, the problem with the central system is that tends to be less flexible as having building blocks to build up your basic system.
Thank you. Could you talk a little bit about, oh, sorry, Peter?
So I just want to mention not to forget about designing for test. And in that regard, the master-slave architecture is advantageous over the centralized architecture. So in a master-slave architecture or in a distributed architecture, you can test the separate modules or boards independently of each other. And so that makes things a little bit easier. A key feature or something else that's beneficial for test, the Nuvation BMS also has edge connectors. It's fully connectorized, so all of the signals that you would want to measure come out through connectors, so you don't need a bed of nails type of test system. And then you can, again, test the separate modules independently.
Thank you. I think you've touched a little bit on my next topic, and it was about how the introduction of scalable BMS platforms impact R&D and deployment costs for future energy storage systems. So I'm asking you guys to scry into the crystal ball a little bit and talk about how those models that you were just discussing impact tomorrow's energy storage systems.
Yeah, I mean, I think what's going on is we continue to put in place additional building blocks in order to enable these future energy storage systems. And so, we've got, analog front-end chips now that we didn't have in the past that enable us to have reliable front-end measurement. We've got battery simulation systems that we didn't have in the past that allow us to have more reliable battery management systems. That ripples up into a level of system engineering that we can put in place, the R&D investment, leverage that across multiple projects. Ultimately, that enables us to build much larger in kilowatt hours and in power battery systems that we built in the past. Because we've got all these unit-tested basic blocks that we've proved across a number of other systems, now we're with customers talking about systems that are measured in tens of megawatt hours, or the unit of measurement of shipping containers. Whereas 10 years ago we didn't have those sort of conversations. We didn't have enough things put in place on a system level in order to, as engineers, be advancing those sort of systems into the public.
Thank you. A question on the testing side. With new cell chemistries constantly being developed, what advantages does battery simulation provide to research and development teams?
So the advantage of cell simulation and hardware-in-the-loop testing is that while chemistries are being developed in R&D, there's also a model. There's a model that is available usually before the cells are developed. And that mathematical model can be used to start development of the BMS and in the design phases of also simulating the pack based on the model characteristics. And you can be designing and testing your BMS in parallel while the pack itself is and the cells are still being developed. And this obviously decreases your time to market.
Thank you. How can low-cost, reliable, long-distance communication, which is necessary for modular BMS systems, be achieved in the presence of strong electromagnetic interference?
I think I can address that, but I might have to step back and say, when we first came out with our battery monitoring devices, we came out with a system in which you could monitor a high voltage stack by taking a bunch of these monitors and connecting them up directly to the battery and then communicating through a daisy chain through a serial line from one device to the next and down to the bottom of the stack. So you can measure many cells. And the original design used a simple serial interface. And also, if you look at most analog front ends today, most of them do something similar. And that's what we did, and we came out with our first part years ago. The basic assumption behind that was that these chips were going to be on the same board, the short distance, which is perfectly suitable, especially for a robust serial interface, which we had in the current mode, or on stacked boards. But what happened, as you mentioned earlier, as we've sort of moved from the initial designs, especially like in automotive, where they put the BMS all on one central design with the batteries, to more of a modular system where it was more flexible. It was a more efficient building block, especially if they're going to have multiple models, multiple battery stacks, and they can just take the number of modules and put them together. But that meant being able to separate modules and put them over distances. So when you have a modular system, you have a group of 8 to 24 cells in a module with some electronics there to measure the cell voltages and then report that back to a primary battery management system. So what you need there is, you're going to need something, as you mentioned, you have noise, so you have to have something that's extremely robust. You're going to have something that is isolated for the high voltages, because now you've got, these modules could be at very high voltages, sufficient to carry enough data to get all this communication, all this measurements out. And for most of these applications, cost is a big deal, so you've got to find a way to do that. So initially, what people were doing to make modules were they're taking these devices and then adding a CAN interface, and mostly because this is automotive and engineers are familiar with it, they put a CAN interface on their module, and then they used that, had to add isolators as well, and this gave them basically a robust, noise-immune, isolated interface, but it's expensive. And what we recognized is that there is a more cost-effective way to do this, and even more noise-immune way to do it, by developing a 2-wire differential interface using transformers to provide the high common mode noise immunity, and also for the high voltage isolation, so that now we can communicate up to 100 meters in automotive environments. And if anybody here has worked in the automotive environment, you know that they've got a standard test called bulk current injection testing, where they just inject current right on your communication line and make sure you can still communicate efficiently. And so we've done that and proven that this 2-wire interface that we developed called ISOSPI actually is able to allow that modular system in the noise environment, and also cost effective. So we were able to integrate that into the IC and minimize the need for CAN and isolators and all that stuff. So.
Thank you.
So to share what that looks like on the ground, so I mean, we're on our 4th generation battery management system now, which uses the ISO-SPI. Our Gen 1 system was exactly what Greg described. It was just a serial interface, not differential, just single-ended. And our test bed that we used was an electric race car that we converted from gas to electric operation. And so we got the battery management system working, sitting there, still on the ground, worked great, very good communication. We take the car out, and every time we'd go into heavy regen braking, we'd lose all communication with the battery management system. We're like, what's going on? And so we hooked up a battery scope to one of the voltage lines in between the boards to see what's going on. It's nominally a 5-volt line. And in the scope, we had to run the test a couple times because it kept clipping. We were getting an excess of 100-volt surge on this 5-volt line, which makes electronics unhappy. It doesn't appreciate that. And so we actually we had to go in and put in all kinds of additional filtering and shielded cables and all this kind of stuff, which we don't need anymore, because now we got better chips with differential communication. So it actually ripples through to not only better communication, but substantial system cost savings, because we don't need to put all the other junk on. So that's kind of what it looks like on the ground. So it's good.
Sounds great. That's awesome. Thanks a lot.